my tap drilled. It is now time to change tools to my tap. Tool 8. Quarter 20. What does the U in UNC stand for?
Unified.
Ooh, man, much props. What's the N? The N was for course. You got ahead of me, didn't you?
Sorry. I thought you said N.
Okay, smart guys. How do we come up with the term unified? Straight from the machinery's handbook, by the way. It has to do during World War II, where we did not have a globally unified thread system. So depending on who was making something, it would or wouldn't fit.
Oh, like the metric system?
Ooh, don't say the metric system.
Oh, sorry.
Yeah, that doesn't exist. Yeah, right. So the inch system was the unified system. The answer to that. All right, so this tool is the longest tool of these three, so I'm definitely going to the side to do this tool change. So definitely put a location off to the side in there. Tool diameter doesn't matter because I'm using it axially. RPM. You are not calculating RPM here. All right, let me take that back. This tool, the manufacturer rates this tool in steel at a certain SFM. The tool can handle more SFM than we're going to throw at it. We are intentionally going to pick 500 RPM because we can't be any higher or this tool is not going to slow down at the bottom of the tap cycle without snapping our tap. So use 500 on these machines. When you get into machines that have rigid tap, you'll use the SFM that the manufacturer gives you. So here we're programming 500. We're turning it clockwise. Use your coolant type. I don't have mist coolant, so I'm going to use cutting oil. And an actual tool change, yes. Accept. Next is our tool path. You'll be insert, cycles, tap, insert, cycles, tap. We have F1 is straight tapping, F2 is tapping a bolt hole circle, F3 is tapping an array, and then F4 is tap, repeat from a previous tapping operation. Here we're going to use F1, tap. Now we will want to toggle to see what our options are. F3, reversing, floating. Now I've already told you about rigid tap and that we don't have it on these machines and we're using a floating tap head. So we know which one we're going to use. But reversing is a cool deal. So there is a tapping adapter that you can put your tap in, and as long as I'm feeding down into my stock, it turns clockwise. As soon as I reverse, this thing reverses direction and starts going counterclockwise. Super cool. Way too expensive for a tech college. So we're going to use our floating tap heads that only cost $300 each.
How much is that one?
I don't know. I haven't even priced one out yet. So floating is what we're using. Our location for our tapped hole. My surface height currently says an inch because I want to prove out my program there. When it's time to cut, I need to come in and bring this down to 0. Clearance height, rapid 2, same, 100 thou. Depth, uh-oh. Time for Uncle Damon's trigonometry lesson again. Actually, this isn't going to be trig. Where's my tap? Let's get my drill out of there. Was that a yawn? That was a yawn, wasn't it? How rude. I'm almost done. Okay, let's get that out of there. Let's see if I can, let's zoom in on this puppy. If I can put something under the back to get it set right. Okay. So, remember on our drill how we had to compensate for the drill point? Well, we have the same conundrum here. The thread call out, if I can get that in the frame, is to have 350 thou of thread depth, actual thread depth. Our situation here is we have it takes us 3 threads before we get to a full thread. So I need to compensate for the tip of this tap. Now, what's the length of the first 3 incomplete threads? Say again? 150 thou. And how did you come up with 150? Because the pitch on a quarter 20 is 50 thou. 3 threads is 3 times 50 is 150. Everybody on board with that? All right, so let's go back to the screen. So my depth is going to be 0.35 plus 0.15. Enter. Now, here's another tidbit of wisdom for you. Thread callouts on prints are minimal depths. Some engineer says this is the fastener that's going in this hole, it needs to fit. You can't be shorter than that. You can be longer, deeper, if it doesn't pass through the back of a part. So if it can't be longer, typically there'll be some note saying so. If you're in a thin part, I've machined thin parts before. You can only have so many threads, or it's poking through the back of the part. So, gosh, they had a fancy name for it. Breakthrough, I think they called it. Okay, in this case, drop my pencil. I'm going to 0 this. So now I need to program the feed of this toolpath. And I program the feed with threads per inch or thread pitch. Why do they put both of those questions there for me? Matter of fact, what is our threads per inch, boys? 20. I put 20 and look, pitch went to 50. Man, don't you love computers? But why do they have both of those there? Head scratcher, head scratcher, head scratcher. Anybody?
Make it easier, you plug in one and it'll...
No, where's my metric man here? It's so I can, when you program metric threads, it's not threads per inch or threads per millimeter, it's the pitch.
Yeah.
1.25, 1.5, right? So here I can program this feed rate in either way by just putting the pitch in there. Now here I would not be programming in inches if I had a metric part. I would change my units of measure to...
This would automatically go to millimeters?
No, I'd have to go into my settings on my machine. So if I wanted to stay in inches, then I would have to sit there and do the conversion, which would take all the love out of the metric system and make it hard like we like to have things, difficult. All right, so here's our feed rate, and then dwell time in seconds at the bottom of the hole. This is going to depend on your machine. This machine liked 0.6. I started at 0.5. I recommend you start at half a second. And then I'm going to show you how to tweak it, what it looks like. Tweaking it. All right. And we're obviously, so I can't even select these bottom ones, guys. Goes right past it because it's grabbing the spindle speed and direction from previous. So here, you're just going to hit accept.